Okay, so it's a pleasure to introduce Randolf Altmeyer, who's going to give our second talk, our last talk in fact today, on polynomial time guarantees for sampling-based posterior inference.
Thank you, Gareth, and hi everyone. I very much appreciate to have the opportunity to speak here. Thank you very much to the organizers. So especially because in a way I'm an imposter as a statistician, but I hope I still can give you some interesting ideas from my point of view on MCMC. Also I still very much, I very much enjoy conversations here. It's fantastic workshop. And I also very much enjoy that it's just a 10 minutes bike ride from home, so I still live in Cambridge. All right, so to get started, the paper is on archive for a while, it's now fully revised and hopefully appears soon. And I should say that the title is quite generic, quite general, and in fact the goals of the talk are more humble. So yes, I will talk about sampling guarantees in a way that we have done so far already in the conference, but the emphasis is very much on polynomial time versus exponential time. So I don't really aim for optimal rates, optimal mixing times, but rather to say when do we have really this regime going to polynomial mixing times compared to exponential. All right, so let's get started. And let's begin by just talking about the basic ideas, because I think this is really what I want you to take away from the talk. So fundamentally, what I want to talk about is how to extend sampling guarantees as we have seen so far in idealistic settings, for instance, where we have smooth concave target measures, to the setting where we have non-concave targets. So I will try to convince you that in many realistic models, statistically speaking, we do not have concave targets. And so how do results that we already have transfer to that setting? And the key ideas are listed here, and I will elaborate on that the rest of the talk. So the key idea, as simple as it sounds, is to find a region where my target behaves well, behaves nicely, in this case locally concave. And then we want to actually not so much, so the goal is really to use then the statistical properties of the target. For instance, having enough data, having nice properties of the Bayesian posterior, which we will look at in this case, to show that the region that we picked out in the beginning is actually relatively large. And large means here relative to the step size of our sampling algorithm. And then finally, we, well, not finally yet, so the next important step is, well, once we know that there is a good region, a region where we have curvature, we still have to find that region. And so the important step is to have a good initializer. And this is more crucial than maybe sometimes is mentioned in talks. So finding a good initializer is hard, but very crucial. And then finally, for sampling, we just use our favorite algorithm. In the talk, it will be unadjusted Langevin. And then run essentially the same sampling, but now with an adjusted target measure. And in this case, for this talk, this target measure will be globally concave. So I kind of want to find a good compactification that's on which my target behaves nicely. All right, so these are the key ideas. I will talk about them now in more detail. But somehow, to put it in the context of the workshop, the way I see this now is that what I'm trying to do here is to show that if I have well, a target measure that has nice local behavior, then after initializing into this nice local behavior, I should expect that a local algorithm, a local sampling algorithm will do well. And if I tell this to any of you, you would probably say, yes, that sounds reasonable. A local algorithm should pick up on local structure. But that this actually works to make it quantitatively correct, and that in the end you obtain polynomial sampling guarantees is not obvious at all at this point. And at least after the talk, hopefully I convinced you that yes, the story does make sense. Okay, so let's get started. Because in the end I want to use properties of the statistical model, I have to elaborate a little bit on the model. But at this point, this is still rather general. So the basic setup is we have to say what is a Bayesian posterior. This is our target measure in the end. So we start with some IID data coming from some density P sub theta. Theta is an unknown parameter. Actually, okay, so this should be theta naught, and theta naught is, you can think of it as something high dimensional or infinite dimensional. It doesn't really matter at this point, but certainly the dimensionality is something that is somehow part of the statistical model. And so the high dimensionality comes into the game because we have to pick a model dimension and then, according to this model dimension, put a prior on the unknown parameter. So the posterior then in this form is essentially the exponential of the log likelihood function plus the log prior, and the log likelihood is just the sum of the log densities. Okay, and everything I will say from now on works on this formalism. So I talk about the log likelihood plus the log prior. All right. So as far as we are concerned here, we are looking at cases where this posterior is not conjugate, doesn't correspond to a known distribution. So we have to use sampling to access posterior quantities like the posterior mean, quantiles, and so on. And there's certainly a trade-off at this point. So don't think of P as something fixed necessarily. So P is something I can choose as a statistician. It depends how many covariates I have, how many features I put in. So technically, I could choose a very, very large P because I want my model to be statistically complex to really get to the truth. So in the end, I want to learn something about the unknown truth. But then, of course, in this case, sampling will be slow because I have a high-dimensional sampling space. So for sampling, I would prefer a smaller P. And in the end, it's all about finding a good trade-off. And so really what is the goal in the end here is to quantify mixing times, not only in terms of the number of steps I need to reach a certain mixing time, but in the end, the mixing time really will depend both on the number of samples, the statistical samples n, and the dimension that I pick for my model. Okay. So here I don't want to be sophisticated in terms of the MCMC algorithm. So I really pick the algorithm that is somehow most straightforward with off-the-shelf results. And here this is the unadjusted Langevin algorithm. We could pick another one, but this is what I choose here. So as we have seen many times, it boils down to this Markov chain that follows essentially the negative gradient of the negative posterior density, log posterior density in this form, and then has this Gaussian innovations. Okay, so we've seen this many times. Fundamentally, if you do not impose any conditions, then this is hard, and this is well known, of course. But let's just go through it quickly. Without any assumptions, this posterior will be multimodal. There's no reason why it shouldn't be if you don't assume anything. And so it can actually take exponentially in n, the number of samples, many steps, to escape from local optima. Because you should think of this as a sum of n terms, and without any further assumptions, this will be of order n. There's no other reason. So the wells that I have, they will be pretty large, and it will take an exponential in n time to explore all these local optima. And then, of course, the dimension is a very important factor, right? If I have too many directions, it will take a long time to explore these directions. So mixing times will generally scale also exponentially in the dimension. And finally, which is really important, initialization becomes very crucial in these general settings, because if you initialize outside of the bulk of the distribution, it might take a long time to reach the bulk of the posterior. And this is actually something you can prove. There are explicit lower bounds that demonstrate that bad initialization can hurt you for sampling. All right. So this sounds bleak, but of course we know that this can be overcome, even in high dimensions. And one way to do that is to assume that our target is nice enough. And nice is quantified here in terms of being having a log density that is negative f here, in this case, is globally smooth and strongly concave. And in this case, it's known that even in a high-dimensional setup, I will have polynomial mixing times. I don't care about the exact constants here. I'm sure many of you know this a lot better than I do. But certainly, the mixing time will depend polynomially on the input dimension and the accuracy that we have asked for. So, and just to put some notation, so in the end, I will mostly talk about the curvature and the Lipschitz constant, all quantified in terms of the Hessian. And a typical example for me, so this is of course very general, but here we talk about posterior sampling, so my f will be the negative log likelihood plus, for instance, for a Gaussian prior, this term here on the right. Okay, so this is the story, but now what I want to tell you next is that in most cases, for such posteriors, these assumptions are not satisfied. And this is now what I will talk about next. And this is a little bit technical, because I really want to make this point come across clearly that while these assumptions are very nice and convenient mathematically, they are very, very atypical. And in the typical cases, neither of these assumptions is satisfied. I'm neither concave nor do I have Lipschitz gradients. All right, so to set this up, and please interrupt me if this is unclear at any point, I will look at the simple regression model. So I have covariates xi and observations yi. Here you can think of the situation that my parameter is actually a function, and this is just to put us back into the non-parametric statistics framework, but it doesn't really matter in the end. This is a finite dimensional parameter, p-dimensional with respect to some basis functions. In the end, it's all about sampling these coefficients, and the covariates are on the domain, and I evaluate essentially this parameter function on the covariates that I have here. Okay, so it's a function sampled along a domain, and then typically models that we look at are generalized linear models. So this in particular covers Gaussian regression, logistic regression, Poisson regression, all the famous examples that we like to use to demonstrate that a sampling algorithm works or not. And so typically we have a link function there that assumes that the mean is somehow mapped into the parameter space. And then the likelihood has a certain form. This doesn't really matter too much. You can just ignore all of that and just realize that the Hessian of the log likelihood is complicated. So for now, this is enough. So particular, it's complicated in the sense, this link function appears very explicitly there, right? So there's this b theta function, so the link function appears here explicitly. And so really computing even gradient steps is expensive. And now showing that you have curvature here is not obvious at first. But let's look at an example where we have curvature. So the first example, the first two examples are actually somehow much simpler. So we choose a canonical link function. And in this case, if we do that, so whatever it's called canonical link, it's not really important at this point, but somehow when you do that, then the Hessian reduces to something very nice. So essentially up to this term here, so this is certainly then positive definite, assuming that this a function is convex, which it is usually. And so you will have, up to the minus, it's negative definite. But so essentially what you have to quantify is how this a function depends on the parameter. And so for logistic regression, for instance, you get this explicit term. For Poisson regression, you get another term. But what I want to say here is, so why this is not difficult? Why does this demonstrate that something goes wrong? So first of all, you see that in order to have curvature, I would need that this is somehow bounded away from 0. But if my parameter can become very large, then this can certainly hit 0. Okay, it's bounded. Okay, fortunately for logistic regression, I will have bounded gradients, but certainly I will not have strong log concavity for the likelihood. And this is an issue that actually matters, and people get around that by essentially combining a logistic regression model with a log concave prior, which then induces some concavity, right? So because my model is concave, it might get 0 at this point. I might have 0 curvature for the statistical part, but the prior will save me. Okay, fair enough. Let's leave it at this for a second. The second example is a bit different. For Poisson regression, somehow hitting 0 is also a problem, right? I mean, if my theta here becomes very negative and large, this is a problem. But certainly, now this one is not even bounded. So if I compute gradients, I also have this exponential term. So the gradients, or the Lipschitz constant for the gradients will explode. Okay? So in these simple examples, I already have somehow demonstrated that you will not have global curvature and global Lipschitz gradients. So this is somehow what I summarize here. So for GLMs with canonical links, this doesn't work. It still works for some models. Yeah, like for logistic regression, if I add a nice prior, then I somehow help because, well, even if the log likelihood is not strongly concave, the prior induces some additional concavity. But this is a little bit of a, and I keep repeating this argument, that somehow this is not how you should think really practically speaking, because as a practitioner, the prior is something you induce to regularize the model, and the prior shouldn't be so big that it somehow washes out the contribution from the data. So making the prior so big that you get a nice curvature and make your sampling faster, makes your sampling faster, but it destroys the statistical message in the end, right? So because you still want to do something with these samples in the end to learn about your actual model. And so you have to be a bit careful. Bayesian, from a Bayesian point of view, the prior should wash out asymptotically. Shouldn't actually contribute anything. Okay, and lastly, and this is maybe, it's just one line, but as soon as I go away from this canonical link situation, then everything breaks down and I have no concavity at all anymore. Think of this very complicated Hessian that I had before. All right, so now you could still question me now. I mean, this is all very nice in a way, but it seems like this could be solved very easily by just restricting to a nice compact set for parameters, right? So this was the problem. I said I have here a problem because if theta becomes very negative, then this hits 0. If theta becomes very large, this hits infinity. So in a way, the problem would be solved if I just find a large ball of parameters and then everything is clear. Yeah, you can do that, and people look at these situations, right? You are essentially well conditioned on a compact, and outside you don't really care so much. So this is one way to go beyond the log concave setting. But somehow the key point is, can we do this in a justifiable way? And do we have to do it, actually? So this will now be the next part. So, but before we come to that, I just want to emphasize that these GLM examples are nice, because this is something people see in practice every day. But this is actually a more generic phenomenon that log concavity doesn't hold for posteriors. And I know people are not super fond of PDE type models, so I don't want to go too much into that. But just to make a point that if I have a model, like a simple Gaussian regression model, I have a complicated regression function here at simple Gaussian errors. This is a Gaussian regression model, where the regression function is actually not the target. So this is an inverse problem where this function is the solution to a PDE. And I'm not actually interested in the u theta, I'm interested in the parameter theta that is hidden in this equation. So in order to find the theta, I have to first estimate u theta and then solve the inverse problem. So inferring theta from such data is a very famous fruit fly problem in nonlinear inverse problems, and is known to be very hard. And hard is because this map that we have to solve, finding parameter theta from u theta, is nonlinear. And so if you look at the log likelihood in the simple Gaussian model, this will be non-concave and the gradients are not Lipschitz. You can prove that. This is simply not true. And so any MCMC algorithm will fail, naively speaking, at this point. And this is something you observe when you run this. So you have to work a bit harder. Okay, so now how can we go beyond that setting that I just discussed? And following up on my key ideas in the beginning, the idea is now to find a local set of curvature that I can exploit. And statistically speaking, there's one fantastic candidate that we can use here, and this is the Fisher information. So the Fisher information is a statistical notion that really describes curvature in a statistical sense. So we know that if we are in a regular model, then regular means exactly that if Fisher information is non-vanishing as positive definite. So the Fisher information is just a negative Hessian of the log density. And here Fisher information really means that I take the expectation at the truth and evaluate it at the truth here. Okay, so this is really what Fisher information means. So fantastic. So we have a quantity that we can actually use to study curvature for our model. But of course, in practice, we don't have access to this because, well, I don't know the truth. and I don't know I don't know the expectation. But there are tricks to get there. And the tricks are two things. So the first one is continuity. That's easy. Essentially, we expect if we go away a little bit from theta not here, then this should still be true, right? Because it's greater than 0. So somehow this should be not too much invalidated. And second, somehow by concentration of measure results, if I have enough data points, then this log likelihood that I have here that depends on n data point should somehow concentrate around its mean. Okay, so I can write down deviation inequalities that tell me that this is not too far away from its expectation. And this is then essentially related to the Fisher information. So at least intuitively, this suggests that we can somehow find a region, a radius, we can find a curvature radius, I call it curvature radius, depending on P and N, such that if I'm close to the true value, then somehow curvature holds. I have a curvature bound, and I have essentially an upper bound on the Lipschitz constant for the gradients. But somehow, of course, this depends on P and N, and we all know that, right? So we always quantify convergence guarantees in terms of the kind of condition number, right? So and they depend on the upper and lower bounds here. All right, but now this is local. The question is, how do I find this radius? But assuming that I can, so the goal is now, this motivates this plan that I have to find a good set where these constants are somehow controlled. They're not really constants, right? They depend on P and N. But somehow on this ball, I'm locally smooth and concave. And then this somehow motivates to build a globally smooth and concave surrogate that I use then for sampling later on. And this surrogate is constructed, or should be constructed, such that on the good set of curvature, I don't do anything different. And then in the end, I just run, for instance, Euler with this adjusted target. Fantastic. I should say that this is not my idea, so this was kind of suggested in a paper by Richard Nickel and Sven Wang here in Cambridge. And I should compare first to what I do. So in a way, what is added in this paper is that this approach that they discussed includes this basic idea of local log concavity, but very much restricted to PDE models. And here I consider general statistical, high-dimensional statistical models, in particular GLM's density estimation, Darcy, and so on. And then what is actually one of the bigger contributions is that I will show in the end that the surrogate construction is not necessary. So if you don't make your model too complex, you can actually get away with standard vanilla Langevin. You don't even have to restrict locally, and I will talk about this. And finally, this is maybe a side remark that the proof is different in the sense that it's fully Bayesian, and I don't talk about the map estimator. But yeah, just to put it on the slide. All right. So let's go through the basic steps before I come back to the example. What are these localizing conditions that I have to impose in order to make this work? So we need two ingredients. The first ingredient, I need this curvature. I need to quantify how much curvature do I have. And second, I need a notion of statistical accuracy. And this is quantified in terms of the rate of contraction. So this is really where the statistics comes in now. And typically, this is the goal, to show us that, in fact, the posterior will live on a much, much smaller set than the set of curvature. This is the fundamental goal in the end. It is not obvious, right? That the posterior, as a complicated measure, will actually have curvature on a large enough set. This is not clear from the start. So let me call this set B, the good set of curvature. Let me call it B. It's the set of all parameters close to. Well, this is kind of a little bit of a trick. So I don't center around the truth, but I center around the best point that I can attain in a p-dimensional approximation space, right? So technically I should put here the truth, but the truth I don't know. I only look at p-dimensional parameters, so I have to find a good parameter here, and I will talk about this now. So essentially, this is what is here. I assume that my space is large enough to statistically say that all the other parameters, all the other coefficients of my infinite dimensional truth can be ignored. So this is a bias condition, a statistical bias condition. So even if you can just ignore this for the rest if you're not interested in the delta n. But in principle, there's a reason where this comes from. It's like a bias variance trade-off in the end. Right, so the bias is controlled here, and the variance is controlled by the rate of contraction and the posterior. Okay, so far so good. Now the next step is, as we discussed before, I want to have local curvature. So the way I do this is to simply require that now my log likelihood has curvature, lower bound and upper bound, and it depends polynomially on the dimension. This is an assumption, and I can verify this in specific examples. But of course, it will always scale in n. There's no way around that, because the log likelihood, remember, is a sum of n terms, so it will always have to scale with n. I can't get around that. This is an assumption, and yeah, you can verify that with techniques I discussed. This is all on my ball of curvature, but then I also assume that my posterior contracts. This is like in a frequentist sense of saying that in frequentist statistics, we say like the sample average is a good estimator. It converges with a good rate of convergence. And in Bayesian statistics, this is the notion of posterior contraction, which essentially says that the posterior concentrates on balls around a certain parameter of radius delta n. So outside of delta n, I can just ignore everything that happens. Right? So in principle, what this says is that statistically, I don't care about parameters outside of this delta n ball, so why should MCMC care about it? This is the way you should think about this. So this gives you a sense of saying that, yeah, I only have to care about parameters in this ball because outside the posterior is essentially 0. There's nothing to sample there.
Sorry, the Cn is the observation?
Yes. Yes, yeah. So the posterior is always a measure that is random, right? It depends on the observed data. And indeed, so this is now, I explicitly model this in here, right? So this is, my target is a random measure. Okay, and then finally, I have to initialize well, right? Because I have to find this good set of curvature. If I can't find it, then I can't do anything with it. And this finding works by finding a good initializer that is computable in suitable time. If I can't compute the initializer in polynomial time, then sampling is lost already at this point. Okay, and finally, yes, okay, I need to have a good enough prior that is log concave. Because essentially what these conditions guarantee is that I obtain curvature already from the statistical part, from the log likelihood, and the prior is just there to not destroy things. Okay, so I just make it log concave as well. All right, so, and now the next step, once I have these conditions, is to actually do what I discussed before. I have to modify my target now. I have to find a good enough approximation that does what I want. And I want to do this in an informed way. So, and informed means that I want to essentially leave the original model unchanged on the good set of curvature, and outside I just concavify brutally. I just cut off essentially. So this is what this line does. So I define now a new log likelihood, a surrogate log likelihood, which does exactly this. So essentially, if I'm inside the ball, then well, the point of these functions is to say that on the ball nothing changes. So this is essentially what happens here. And outside on the ball, I just cut it off. I just make sure that only this convex function negative, the convex function here matters outside of the ball. And so what you can prove then is that this function is then globally concave and satisfies the appropriate upper and lower bounds on the Hessian. Okay, so far so good. So in a way, nothing has happened yet. Because even before I define this, it doesn't mean that it's a good thing to do, right? So I mean, I can define loads of surrogate functions, but who says this is a good one? So I still have to convince you of that. But once I have the surrogate, I then just run ULA with the surrogate and hope that things work out. But of course, I make a mistake here, I make an error, because now I'm not sampling anymore from the true posterior. Now I'm sampling from a surrogate posterior. This is a new function, a new density. So yes, maybe this, from an applied point of view, we hope we didn't make much of an error, but just concavifying outside of a large set. But statistically, this is a difference. So you still can draw the same conclusions in the end. So you have to verify this. And what I also want to mention is that this is an approximation, but it's not an approximation as you would see in other areas. So often people look at Laplace approximations. They take the posterior and say, well, this is approximately Gaussian, Bernstein von Mises theorem, and so on. So I can do a Laplace approximation, which means to replace the posterior by a suitable Gaussian with a nice covariance matrix. This is not it. This is a log concave approximation. So in a way, it's a different space of functions where I approximate. Okay. Okay. Before stating the final result, the results, let me just make clear that how to do this in a specific example that we discussed before, and to convince you that actually things get better by doing this. And the example is again back to the GLMs. So to be a little more precise, now I have to instantiate all these quantities that we introduced. So essentially, my target now, I have to assume it has a certain smoothness in order to talk about this bias condition that I had, right? So statistically speaking, the first p coordinates should do a job, and then the rest shouldn't be too big. So in order to quantify that the rest is not too big, I need to have some regularity assumptions. So this is very standard in statistics. I assume in this case that the rate of convergence that I have, this delta n, is like n to the minus alpha over 2 alpha plus 1. Again, this is a standard rate. The minimax rate essentially for estimating the truth in a non-parametric setup. But for us here, it's just a delta n that I fix. It doesn't matter where it comes from. And the dimension is fixed. So I don't play with the dimension here. The dimension is something the statistician tells me to work with, and so MCMC has to work with that. Okay. This is high dimensional. It's not p equal to n, but it's high. So if n is high, then p is high. As prior, I choose a Gaussian prior, standard. Many people would just, well, if they do Euler, then they will probably also do a Gaussian prior. So I guess it's fair enough to do that. And as prior, I essentially say that I have like decaying variances on the coefficients. So I say the earlier coefficients are more important. Okay, so this is then my log likelihood, my posterior log likelihood, my posterior density, apologies, for this generalized linear model. And so somehow this line is what you would do if you wouldn't listen to this talk. So remember, if we have a canonical link, so here we use a canonical link, let's take that. Canonical link, then the curvature from this part, I try to convince you, doesn't play a role. So all the curvature I get comes from this part. And so as curvature, I get this. Why there is a p here, I don't really want to tell you now, but sometimes it makes sense to have a rescaled prior. And in the end, it doesn't really make a difference because it will cancel out here anyway, right, if I take the ratio. But there has to be a p here from statistical point of view. It's just a rescaling of the prior, why not? But anyway, so all the curvature, the curvature that I get for this comes from the prior, and it's just p. And the Lipschitz constant, the Lipschitz constant for the gradients scales like np. So now if we think of the condition number, then the condition number would be n. Fair enough, this is what it is. Okay, so now I want to convince you that using my surrogate I get a better condition number. So first of all, the condition number in the end will be square root p, which is much smaller, because my p is less than n. How I get there, let me just walk you through, because I think this is relevant. Like, where do I get my ball of curvature from? This is not completely obvious. So the way this works is to say I have to find a ball where if I restrict my parameters to that ball, I have curvature. And remember, in the GLM setting, the problem was that my parameters can become too big or can become too small, too negative. So somehow I have to restrict to a nice compact set. And so as soon as I have a compact set, so as soon as the infinity norm is bounded, somehow things will be safe. This is kind of what I want to say. So the reason I want to choose my eta ball is to make sure that my parameters live in a nice compact. And so I choose here 1 over square root p, because if I do that, well, then I can smuggle in the the theta star p on both ends, right? And then if I know that I live in a 1 over square root p ball, then, well, I just upper bound the infinity norm by the L2 norm up to introducing a factor of square root p, which is then cancelled by this being less than 1 over square root p. And for the second part, I just know that my original truth lives in a nice Sobolev space, has nicely bounded components, and so all is good. Okay. This may look simple, but somehow this is the general idea. So I have to find a nice ball that allows me to control parameters of my model in this way. And this is similar for the nonlinear inverse problems. All right, and if I do that, so then you can go through the calculations. So now this n is much larger than the one we had before, right? So here we had p for the curvature because it came only from the prior. But now here, actually this is much larger because I take the curvature not from the prior, but the curvature from the log likelihood, which is much larger, in fact. So I hope I can convince you that ignoring the contribution of the log likelihood is ignoring this very large curvature that is induced. So in the end, the mixing time will be much faster for the surrogate than using off-the-shelf methods for the original log likelihood. This is kind of my message here. Yeah, and finally, again, somehow at the very end, you have to initialize well. So this is now in the paper, only in the last round in a way, because before I didn't have an initializer, and now I proved that one exists using gradient descent. So you can find actually a suitable initializer that initializes into this ball in polynomial time.
Sorry, I have what you just said before. So if you don't use the surrogate, but maybe this is where you go after that. Okay, we believe that it's going to be slow, but the curvature is already there. So I mean, the stupid things would converge very fast. It's
correct.
Just that we just haven't seen that it would converge fast, and no.
I mean, so okay, so certainly using this, it will still converge. You still have polynomial guarantees, right? That will work.
Yeah, but there is guarantees, and there is does it converge in truth? And the
correct.
In truth, your bounds after that, after in the next slide, are already there. We just don't see them because
correct.
we didn't use your localization.
Correct. That's what I want to say. So I mean, I don't have simulations here to convince you that indeed you obtain the better rates, because even for that I don't have optimality in this case. So the proofs are in a way they are rigorous, but there are lots of constants floating around. So I wouldn't really too much believe in. So this is really a story about exponential versus polynomial time guarantees. And I'm not insisting that any of my upper and lower upper bounds are optimal in any way. But certainly they are better than this. This is already nice. Right, and yeah, so initialization is important. And then, of course, everything I just discussed for the local conditions will still work if I'm in a more antagonistic setting, but classical results will not apply anymore. So the localization somehow saves me here. Okay, so let me give you the main results. The first one is to say that indeed the surrogate posterior is a good approximation. So remember, it's a log concave approximation, but that it actually works is something you have to prove, and somehow this is the result. There are some conditions, additional conditions that I don't really want to discuss much, but there is a model upper bound. And this upper bound is very much related to the fact that I have to use empirical processes at some point to have concentration of measure. So in order to relate the log likelihood or the Hessian to the Fisher information, I need concentration. And this concentration doesn't hold for all p. So this is really a technical limitation. But if you don't go too high dimensional, then at least you can show that you have an exponentially good approximation actually in Wasserstein distance. And then from that, essentially you can take now off-the-shelf methods to say that indeed I have mixing times that scale polynomials. So first of all, I have essentially I approximate the if I have, this is my Euler algorithm with the surrogate, I approximate the actual posterior well in a nice mixing time, using a nice mixing time which depends polynomially on the number of samples, the dimension, and the accuracy. And finally, then you can also use that to obtain guarantees on functionals, which from a statistical point of view is important because you want to estimate, for instance, the posterior mean, and this is what this gives you. It's all very explicit, but of course there are always some constants floating around. Okay, so the final part, which is, I think, interesting, is to show that what happens if I don't want to do the surrogate. So this is now a bit different. The story is as follows. So this is vanilla ULA, where I start with my original log likelihood. This is the surrogate ULA, where I have my surrogate log likelihood. As long as they both start from the same place, and as long as I don't leave the ball of good curvature, they both do the same thing, right? So by construction, these two chains will coincide as long as I haven't left the ball of curvature, of good curvature. So the question is, how long does it take to leave this good set? So this is, in principle, just an exit time problem. So let me tell you how I worked on this. So essentially, if I'm in continuous time, things are easier, right? So I can essentially write down the continuous time formulation of ULA. And of course, as long as I'm in the set of good, as long as I'm in the good set, this is just the log likelihood. So I know this very well, this object. I don't have to concavify. And then I compare this to an Ornstein-Uhlenbeck process with the right curvature. So this M is indeed the curvature bound that I get for the full potential here. And so this is just a comparison argument for Ito processes to upper bound essentially the question, when does my continuous time Langevin chain leave the nice ball? Well, this is certainly after, this happens certainly after I have left this nice ball with my Ornstein-Uhlenbeck process. And so in the end, what you have to do is to use exit time bounds for the Ornstein-Uhlenbeck process, and then you have to bound the discretization error for the Euler discretization of this continuous time process. Yeah, so this is, in a way, it's very classical, but it's interesting that it works out in such a nice way, because what you get in the end is the following. So the result says that my stopping time, the probability that my stopping time hits before a given time j is less than a probability, so it's less than essentially this right-hand side, which has my j here and has here well, terms that depend on the radius, m, and the dimension. So what does this mean? So typically, in the examples that are important for me, this bound will essentially be larger than n delta n squared, and this is something that, with the exponential, then decays exponentially fast. Okay, so all you have to take away from this is that this right-hand side, at least this term here, becomes very, very small very quickly, if n and p are large. So what this says is that as long as j is not too large, the right-hand side will still be very tiny, right? So in other words, as long as I don't run more steps than somehow killing this exponential term here, the right-hand side will still be tiny, and so as long as this is tiny, my vanilla ULA actually coincides with the surrogate ULA. So I have the same convergence guarantees that I had from before applying to the vanilla ULA. Okay? Because I will not be able to do exponentially many steps in the end. So, I mean, this is why we talk about polynomial versus exponential, because polynomial can still be a long time, right? But at least I will not be able to run exponentially many ULA steps. So as long as I don't do that, which I don't do, if I restrict like this, then the sampling guarantees apply. There are some caveats, and one caveat is I have to reduce the step size dramatically. And there are some other conditions which I didn't write down here. So in fact, I have to make my model still a little bit smaller. I cannot achieve this optimal model dimension that I had before, right? So in the example that I had, I picked my model dimension like this. And so for the surrogate, I get here the nice rates. But in order to apply this to the vanilla algorithm, I need to restrict the model dimension a little bit more, so I don't attain the optimal rate of convergence, statistically speaking. But nevertheless, so essentially this one shows that I don't have to do this restriction because somehow it's inbuilt in the algorithm that I will already do the right thing. Okay, fantastic. So let me just discuss a few things shortly. So essentially, the main difference to other similar algorithms for high-dimensional models is that this is a log-concave approximation. There's no Laplace approximation. There is no Banach-Von-Mises. This is all down to earth in that sense. And it's still honest in the sense that I'm still sampling from the true posterior and not like in variational base from some close but not statistically valid approximation maybe. And then so the proof itself also holds when there is no BVM. This is important because there are situations where there is no Banach-Von-Mises theorem and you can still apply this. And finally, initialization is fundamentally important. So in summary again, as long as I can initialize well, a local sampling algorithm will do well for local statistical models as long as I have enough data. This is essentially the story here. And this is my take-home message, which has somehow not managed to actually take the take-home message in the same box. So as I said, so as long as I can initialize well into a region of local curvature, and the curvature constants depend polynomial and NNP, this is what I had here, then in fact vanilla Euler will compute posterior aspects in general high statistical models, high-dimensional statistical models at polynomial cost. This is kind of the story. Yeah, so the paper has lots of examples, and I think this somehow really shows that local algorithms can work well, but it doesn't mean we shouldn't go beyond that. So I fully agree with many of my previous speakers that this is not the end of the story, but at least this explains that all the hard work we have done, or that you have done for studying log-concave sampling problems, indeed already solves a big chunk of statistical problems of interest. So yeah, many thanks for your attention.
Thanks very much, Randolph. Do we have any questions?
So at some time you said that this condition of p less than n divided square was optimal. Is it a statement like you have a negative result, which is if you take p too large with n, then you don't have that with high probability, you have positive curvature or something like that?
Very good question. No, I don't. That would be fantastic, because essentially, as soon as you invalidate this condition, the statistical part, the log likelihood part, can become dominated by the prior part. So this condition somehow saves me a little bit. Yeah, so it would be fantastic to go beyond that, but it's technically tricky because the proofs really rely on this.
Maybe I missed it, but does the step size in your Euler, does that not need to shrink with your contraction rate?
Yes, so it's the standard. So whenever I didn't mention it, it's the standard condition. So okay. Whatever, what is it, 2 over m plus l, what is usually. So, and only when I mention it, it has to shrink faster. But yes, it has to shrink.
I see.
Yeah, absolutely correct.
Any more questions? Yes, one more.
It was good again, so good to see the talk the second time. So if you were to study things at fixed p,
yeah.
Do you think you could show something like your sort of the effective condition number of the algorithm is going to 1, basically? So you step away from the high dimensional setting and you just say, with this localization trick, am I actually gonna, it would kind of be like an algorithmic BVM in a way.
For fixed dimension.
Yeah, fixed p and going to infinity.
Right.
Am I basically sampling from the Laplace on the algorithmic side?
Correct. I guess this is what it will boil down to. Because if you have a finite dimensional model, typically a Banach-Von-Mises theorem will hold. Yeah. And so you will become asymptotically Gaussian. And so this would be a quantitative way to verify this. Correct. Yeah. As long as the efficient information is regular. So I guess probably you're right here.
You are Gaussian, but are you isotropic Gaussian?
Yeah.
Okay.
Okay, let's thank again Randolph and Frank.